Our book talks about four different types of work, and they have, four specific equations. And reality is they pretty much derive off the same equation that we've started with, and that is that work is equal to force times distance. Okay, and for work in a straight line, or if we look at, you know, what's happening here with this picture, say, how this guy's pushing a shopping cart with a force that's directed this way, and it's displacing this way as well, with a displacement or distance this way, okay, in that direction. So what the equation for work in a straight line is essentially what we've started off with. Work is equal to force times distance or displacement. Again, I'm using delta x. Smelter-Schwab's class, you're using force times L for distance. It makes no difference. It's the same. It's essentially the same equation in what we're dealing with. Okay, so this is our first equation. Work is equal to force times distance. Okay, straight line. Okay, the force is acting in the same direction, in the same plane as the distance it's moving. And the reason why we specify it's got to be acting in the same direction or on the same plane is because we've got another type of work, and that is work at an angle. Okay, you can see this guy is pulling on his luggage here. Okay, at an angle. Okay, at an angle with the horizontal. Okay, so essentially what you have here is, let's use a different color. You've got his applied force is this way at some angle from the horizontal. Okay, here's the horizontal. Okay, he's got it acting at some angle here. We call that angle theta. That's a little difficult to see. So let's change the color here. That's difficult to see too. Let's try blue. We're good enough. Theta. Okay, this angle theta. Okay, and he's going to move it some displacement. It's going to move this way. Some displacement or distance. Okay, so it's going to move some displacement this way with this force. Now, the force has to act in the same plane as the distance in order for work to be done. So this angle being this force acting at an angle is made up into components. We know this because it's a two-dimensional force acting in two dimensions. Okay, it's got a y component and an x component. Okay, if we broke this vector up into components, it would have a y component and an x component. Okay. Okay, I've drawn in the vectors. You have your x component, your force in the x direction, and y direction. And it turns out that the y component of this force isn't doing any work. Okay, the reason why it's not doing any work is this component of the force isn't moving it. Okay, it's not lifting off the ground. There's no displacement of this bag in that y direction. So this part of the force isn't doing any work. Okay, the only thing that's doing work is this x component. Okay, and we know that from our previous learning that to get that x component, you take the force, the magnitude of the force, and multiply it by the cosine of the angle. Okay, recall. Okay, recall. That the x component is force times cosine of theta. Okay, cosine of theta. That's going to get our force x. So when it comes to terms of work, work is equal to the force that's acting in the same plane. So that's the x component. So it's the force x times the displacement, or the distance that it's moving in that direction. Okay? And what the book does and what we do in physics is we take this and expand it to get an equation for work at an angle is equal to work times whatever the force is times the cosine of the angle times however far it moves, the distance, the displacement. Now, this is also known as the work in general formula. Okay, this is work in general. If you look back to this example, what's the angle of this force? Well, this force is acting at a angle equal to 0 degrees. Okay, or you could say, or it could be acting at 180 degrees. But let's just take it as 0 degrees. Well, force, if we had that cosine in here, okay, if we looked at the next equation, work at an angle, well, if the angle was 0, as it is here, what would you get? Cosine of 0 is equal to 1, which means force times distance. Okay, so that's another thing to think about. That's why we can use work in a straight line, and we can simplify it to this. And in actuality, this is the more general equation for work. When we talk about work done against gravity, okay, or some people will define it as work done in overcoming gravity, is another way to think about it. One thing you need to realize is, okay, well, now we're moving in the y direction, and in the y direction you may use delta y for the displacement in the y. We're going to just use h, okay, h for height, okay. This thing, you're going to move this from the ground to the top. You're doing this against gravity, so the work is equal to, well, what are you lifting? You're lifting a weight. I know in my class we use FW for weight. Okay, the force weight is essentially uh, what the force that you're overcoming, force weight times the height. And we can generalize this even more, or excuse me, we can expand upon this more. Force weight, or force of gravity, is equal to mg. Okay, so this is mg. The work done in overcoming gravity is equal to your mass times the gravity times height. That's work. The work done against gravity. Okay. The last one's work done overcoming friction. So, let's look at this example here. It's a fairly simple, if we look at this as ground, it's a fairly simple free body diagram where we've got force, that's terrible, force normal acting perpendicular to the surface. Okay, we've got this guy is applying a force applied in that direction. And force of friction acts against the motion, so you've got force of friction acting this way. Okay, and you've got, obviously everything has force weight. So if we looked at our free body diagram, this is what we'd look like. And I know nomenclature might be a little different between me and Smeltzer-Schwab's class. I know you guys, they use N for force normal and W for weight. I just add a little F in front of it just to clarify it for myself. And if we're talking about the work done in overcoming friction, uh, well, we start with our general formula. We've got work equals force times the distance. I use delta x. Again, it's just my nomenclature. Force equals work equals force times distance. Well, we're talking about friction here specifically. So we're specifying that it's friction. So work to overcome the force of friction times the distance. Well, how do we define force of friction? Well, work equals force of friction is equal to the coefficient times force normal times how far it moved, the distance. Okay, and we're going to leave it as force normal. Some people can expand upon it and call it, if it's on flat level ground, we can say force normal is equal to force weight, and we can say mu mg times the distance. I don't like to do that because sometimes we've got a situation where, we might be going up a ramp. So in that case, force normal doesn't equal force weight. So I usually end it right here. Now, what kind of coefficient are we talking about? Well, if we're doing work, the thing's moving, so it's kinetic, not static. So coefficient of kinetic friction times force normal times the distance you move it. That's the work done to overcome friction. And in the next video, I'll start doing some examples uh, from examples from the book.